Yes, so in the previous class we were discussing about your singlet oxygen and the reactions, right. So, in this class what we will do is that we will see some important organic reactive intermediates, we will study some important organic reactive intermediates, right. So, in this class we will be understanding some organic intermediates, their synthesis and their reactions and structures. So, basically I am going to deal with carbenes. Another class of reactive intermediates is your nitrenes. So, we will study carbenes as well as nitrenes. So, initially we will discuss about carbenes. Okay. So, you know about carbenes much because you have studied in detail earlier. We will see from photochemistry point of view how we can understand carbenes. Okay. This is your simplest carbene, right. So, that is your methylene, right, we call them as a methylene or it is the simplest carbene. Seeing this structure, can we write some salient feature based on the structure. Okay. So, what about your carbon now? Your carbon is type of neutral, right. It's in carbene most of the time your carbon atom is neutral and you call them as, that is why they are uncharged. First thing you can say it is an uncharged species. The second thing you can seeing the structure you have, can you guess anything? It's divalent, you can say it is divalent, right. Another thing you can say that the central carbon atom is surrounded by sextet of electrons, right, just by the structure. I am not. So, a central carbon is surrounded by sextet of electrons and it is an, finally you can say that it is an electron deficient species. Just refreshing what you have studied earlier. Okay. So, your carbenes, the central carbon atom it is neutral. So, it is more or less it is an uncharged species, it is a divalent and the central carbon is surrounded by your 6 electrons. So, sextet electrons and it is a type of an electron deficient species. Okay. Now, coming to this 2 electrons. Okay. Now, if I introduce spin, I will just put like 2 dots there. If I write it in the spin, okay, then there is 2 ways I can write the spin, because these are more like a p orbital, right. So, I can write the spin in 2 ways. One, I can write the spin in this direction or I can write the spin like this. Fine, just generally. So, what is this one? So, it should be, because we know that if it is paired we call it as singlet and if it is we call it as triplet. So, we call them as a singlet carbene, you can call this as a triplet carbene. If you see their hybridization, if it is in singlet, okay, it is how it will be in the p orbital. If it is, what hybridization it takes place? sp2. So, you have a sp2 hybridized in singlet. In triplet, it should be sp hybridized. So, if it is sp2 hybridized, then what should be the structure? It should be trigonal planar, right? And this should be, if it is sp, most of the time your carbene is linear. There are cases where it is bent also, but linear you can see most of the time. If you want to draw the structures of carbene, can write this way for to be is trigonal planar. For linear, I can think of I can write like this to be linear. Alright, so singlet carbene is sp2 hybridized, trigonal planar, triplet is sp hybridized and linear or bent. This is about their structure, right. So, the structure we now we know it is trigonal planar and another is linear. Any reactivity point of view, how this should be, how this should be? Triplet should be, yeah, but how they react, nature, whether it is nucleophilic or, so singlet is electrophilic, right. And your triplet is, yeah, it is a diradical. So, that is how you can at least view your triplet and singlets. Okay. Singlet is more like an electrophilic, most of the reaction works like electrophilic. Triplet you work with your radical chemistry. Okay. Yeah, there are cases, but their character is more like an electrophilic. Okay. Fine. Now, what we will do is that we will take individual singlet carbene and see is synthesis, how we can generate, rather than synthesis we call it them, how we generate singlet carbene, then how singlet carbene does reaction. Then we will say triplet carbene, how we can generate, how we can see do the, how it does chemical reactions. So, we will start with singlet now. Any idea how we can generate singlet carbene? Huh? Okay. General synthesis. Which compound you like to use? Yes, you can take your diazo compounds, right. Take your diazo compound, you can photolize or you can even thermalize. Okay. If you heat also it works. So, you end up with singlet carbene plus nitrogen. I hope that you have studied all these things, just we want to refresh it back. Okay. So, you get it idea. Any other synthesis which you think, yeah, from ketene you can synthesize, right. Again you can take a ketene, you photolize them, So, you get your singlet carbene. Fine. There is one reaction which you have studied in your bachelor's, name reaction, but it is not exactly carbene, but you have studied that. What is that? Regularly you use that. Simon Smith reagent, right? So, what is about that? Simon Smith? Yeah, you take a CS2I2, then what reagent it is? Yes, you take zinc copper in ether. So, one thing here it has one difference is zinc iodide, yeah, zinc iodide. What you call this particular one? It is a carbenoid. That is why I want to recollect you that it is not exactly carbene, okay, it is a carbenoid. We call this as a carbenoid. It works generally like carbene, all its reactions and everything is more like carbene, but once you go to its selectivity, you can differentiate this from carbene. Okay, this is Smith. This 3, but majorly this 2 one you use. Normally you take a regularly if you use in lab, you take diazomethane, you photolyze, you end up with a singlet carbene. Nothing hard reaction, it is a very simple one. Okay, ketene also you can do, it works fine, but this one is more like a carbenoid, not like carbene chemistry. Yeah, dichlorocarbene is also carbene. Okay, it is not that see I am just making this R, okay, it can be anything. Now, we will see the reactions of singlet carbene. So, that is how you can generate them. Reactions singlet carbene, which is very good reactions which use yeah, that is addition to alkenes, that is there, but more than that which you have not seen other chemistry does, other species, this does very fast, this reaction. Yeah, insertion into a sigma bond. Okay, very characteristic feature of your carbene. If you have a system like I have an alkane, okay, where I cannot do anything, if you can by any chance if you can generate by means you can generate the singlet carbene, okay, it nicely gets inserted into this sigma bond. So, you will end up like C H. Very nice chemistry of singlet carbene, and it does very fast. Okay. Only problem with singlet carbene insertion is that it is very random. Okay, there is no much selectivity there. If you have like secondary, tertiary or primary, it inserts randomly. There is no selectivity it has. Okay, that point you should remember when you talk about insertion into sigma bond. Why I am saying that when I go to nitrene, okay, singlet nitrene does this reaction much more selectively, but carbene does not do that. It just randomly inserts into CH bonds. It has no big selectivity. Fine. That is the first point you have to remember. The second reaction, as you said, it is addition to your pi system. A singlet carbene with my alkene. See, I am not discussing anything right now about the stereochemistry. Okay, when I go to triplet carbene, I will discuss the stereochemistry. Right now, you just think that yes, singlet carbene can add to your pi system. Okay, it nicely forms a cyclopropane. Yeah, it is very stereo specific, where I will discuss when I talk with triplet carbene. That is another second reaction. So, these are very common, insertion into a sigma bond and addition to pi system. Why insertion to sigma bond is much more used, like nitrene mate is used a lot. It is very famous, insertion into sigma bond. Why? Any idea? That reaction has become like very catchy nowadays, because you can insert into peptides. Okay, you have a peptide, you want to insert a N connected some fluorophore which is nitrogen, then you can take a peptide, generate a singlet nitrene, or it just inserts into a peptide and the peptide becomes fluorophore, it becomes fluorescent. Then you can watch what happens to that peptide, how it interacts with the cell and everything. Okay. So, that is why that insertion has become very more catchy nowadays, fine, which you do much in nitrenes. Then any other reactions, you can see this intramolecular which happens. Like for example, I have a CH3. You can call this an hydrogen shift, or you can call this intramolecular. Anyway, you have this one. I have generated a carbene here. Okay. What you can think it can do? Any idea what it can do? I have a carbene here, okay, which you have studied in most of your chemistry. It nicely take this hydrogen, this 1,2 hydrogen shifts, all these things you can see, rearrangement reactions, all this you can see. Okay. So, if this hydrogen moves across this, okay, I take this hydrogen out somewhere and you can get your chemistry like this. So, you will end up with CH3. You can do this, fine, or you can take this hydrogen also, that is also fissile. Okay. That also you get product CH3, CH3. Can get this also. It does nice 1,2 hydrogen shifts. We call as intramolecular reactions. Yeah, because this is singlet, yeah? I can push my 2 electrons to pick this hydrogen out. Then I can push this double bond to make an alkene. Okay. It is not triplet, it is singlet. Huh? Triplet also it happens. Triplet also does nice hydrogen abstraction reactions, but that is mechanism is different. Any other reactions which you can remember carbene does? Because this 3 you have studied. Okay. You have studied insertion to CH bond, you have studied your addition to pi system, intramolecular reactions, any other which you have studied? I will study dimerization. Carbene does nice dimerization reactions also. Like for example, if I take an azo compound, type of azo compound, yeah. Okay. Based on the same azo compound, I have generated a carbene R2C dot. So, I have generated a carbene using the same compound, okay, and this carbene waits till it sees another molecule, okay. It forms a get this, okay, and this nitrogen goes off, giving this reaction product. That also carbene does. See, this type of chemistry, when you can think about when there is no hydrogen source, when you are doing photolysis and that photolysis does not have any hydrogen source. For example, I am doing this chemistry in benzene, okay, then it does not do anything. There is no chance of hydrogen abstraction or anything, insertion into sigma bond, then it does just dimerization reactions. Okay, that is good. Now, recently people are using this carbene chemistry where in petrol industry for crackings, study that cracking purpose. See, if I want to crack this, break this into, okay, what I am going to do, I am just going to generate a carbene. What it can do? What, sir? I am missing some. No. So, it can easily so I can get my olefin plus. This type of cracking reactions are nowadays started, because you just have to generate carbene, that is all. Because you know cracking may what advantage you get a lot of heat, because you can think about then fuel and all these things. Slowly started up this chemistry, cracking reactions. Okay, fine. One more interesting reaction is there. What is that? Carbene, which I have left. Yes, sir. One more reaction which I left. Synthetic use, it has lot of synthetic application. Methylation, yes, you have that addition, you can do methylation, but that is addition to pi system you can talk about. Okay, that you can think about. Yes, another one, you can make this ylides, okay, because you know ylide synthetic utility is so high. You have studied about ylides, sulfur ylides, phosphorus ylides and all this, and after making ylides you can do n number of products. Okay, that you can do with carbenes. So, if I am singlet carbene, I have and just example I take an X and Y. Okay. Yeah, I can think of my carbene with this. This you can make if my it's a type of an halide. Then I can push this Y. Okay, to give me R2C, X and Y. This normally you can do this type of halides. Okay, slowly started up doing these chemistries. See, normally which you study is basically three important reactions you study on carbenes, which you can remember. One is your insertion to sigma bond, another is your addition to pi system, then dimerization reactions. Okay, these are very common in carbene. If you take carbene reaction, this happens very fast. Okay, that should be your in mind. Okay, these three reactions. Then how to synthesize them? Take a diazomethane, you get singlet carbene, or you can even take carbenes, ketenes, and you can get your carbenes. Fine. This is more about singlet carbene. Now we will go and see what happens with triplet. How you can generate triplet carbenes? Photolysis under inert gas. Very good. That's a very good thing. Then that's a very good photolysis under inert conditions. You can do that. Yeah, if you take, see for example, I am taking a diazometer, and if I photolyze, you know that definitely you will end up with a singlet. Okay, but if your condition is inert, like you are doing this in argon atmosphere, okay, and that's one, and if you can do it in low temperature, okay, then it is also possible. Then if you try to do in gaseous phase, you do it in low pressure also. If you have all this criteria, okay, you can make your triplet carbene. So, there are many criteria. You can do it inert, you can do it in low temperature, low pressure, gaseous phase, you all get your triplet carbene. Any direct evidence that you say that I got triplet carbene? Okay, I ask you to go to the lab, make you triplet carbene, and you can say that I have made triplet carbene. Oh, direct evidence. I am not doing, I do not want you to do one more reaction. Directly, sir, I have made triplet carbene. That is again doing a reaction, right? Any direct evidence you can think about? Yes. So, triplet carbenes are what? How they look like triplet carbenes? Diradical or anything? Yeah, I want one more word on that. Triplet carbenes are paramagnetic, right? If it is paramagnetic, then you know that you can do by EPR. You can observe them in EPR. Will be a direct evidence. Okay. What is advantage? See, if I can make a stable triplet carbene or stable triplet nitrene, for example, you think any advantage it has? If I can make a stable triplet carbene, a carbene which can be stable for at least 6 months, triplet carbene in solid state, you think can we do any application across that? That is why a lot of work is done on stabilization of carbenes, which I am not going to deal, which you have studied. You can stabilize carbene by resonance effect and substituent effects and all these things. If I make a carbene stable, triplet, particularly triplet carbenes stable, what advantage I can? Propagel. Okay, that is reaction point. See, triplet carbene, since it is a paramagnetic, it is highly, it is an organic magnet. Okay, it is a very good organic magnet. You have seen inorganic magnets. See, advantage of organic magnets, because this will be a magnet. Okay, if it is stable for 6 months or whatever, it will be a very good magnet. And organic magnets are light, they are highly flexible. Okay, then I can design some screens. So, if you see this type of screens in TVs, they are more or like flat. Okay, they are not flexible. Okay, if you can think about an organic magnet, okay, for which can sustain for a longer time, then you can think about a screen which can be even flexible. It does not need to be flat all the time. Okay, it can be flexible also. Then you can have your TV in your hand like a watch. Okay. So, that is why a lot of work has been right now is working on triplet nitrenes and triplet carbenes particularly to make them stable for longer time. The only problem is that the stability. Okay. So, if you can make them stable for at least 6 years or whatever it is in many ways, then you are ending up with a very good organic magnets, okay, which you can think about then making chips and electronic device and all these things. So, that advantage this has, right. The second part is that why the singlet carbene just undergoes a sort of intersystem crossing to triplet carbene. Normally, if you see this is triplet and this is singlet, this energy gap from singlet to triplet is more or less very small, that is 9 kilocalories per mole, that is all. Okay. So, that is why in low temperature it just moves down to triplet, the energy gap is very small. Even there are cases where it is 6 kilocalories per mole. So, it is range between 6 to 9 kilocalories per mole. Okay. So, you can always push your carbenes from your singlet to triplet. Okay. So, that is synthesis generations of triplet carbenes. Then we can see the reaction. We will discuss this particular reaction, that is, I have an just for example, I have a system in carbene like this. Okay. So, I can just concertedly add this, it will be a very concerted process. I can just add to this and I can add to this. So, my reaction will be stereo specific, right, because there is no, it is a very concerted process, this to this and this to this, or you can push your 2 electrons and then push it back, that also you can do. So, it is a highly concerted process. So, your stereochemistry is most of the time is preserved. What carbene is this? Singlet, yes. See, anywhere people will ask this question most of the time. Okay. So, fine. If I have a triplet, so what happens? So, if it is a triplet, then I will end up like this, right. Yeah, you can put it the other way around also, but both the spin will be same. Okay. It can be like this or it can be like this, but the spin will be most of the time same. So, now what happens? So, you get a proper spin inversion followed by rotation. So, your whole stereochemistry is now lost, right. So, now you end up with both cis and trans. You can get both cis plus trans. That is very important about singlet and triplet. That is how you know it is one going by radical chemistry and another going by more like an electrophilic. Okay. One more reaction which triplet carbene does, which you should know, it is a simple, it is called hydrogen abstraction. Can get this to C, you can get an H here and with a dot here, plus you can end up with R dot. This is just an idea. See, this reaction is little bit important in one sense, like you should know. See, if I have taken for example, yeah, same like CS2 in toluene. See, hydrogen abstraction process is little bit hard. Okay, it needs a very good lifetime for a molecule to go abstract an hydrogen. See, that's what that's a very important thing. That tells you like you can stabilize triplet carbenes. See, singlet carbene lifetime is very fast. Once you generate singlet carbene, it reacts like this. So it's not a long lived intermediate. But if you think about triplet carbenes, they are long lived intermediates, because these are the reactions which tell that it is a long lived, because it stays in the solution, it finds a counterpart, and it has to unabstract an hydrogen. Okay. So, if it does that, you will end up with type of bibenzyl, which you can see lot. Very important reaction, which your singlet carbene never does. It all depends upon the lifetime. It has to stay in the solution to pick that hydrogen, and it does in toluene very good. Fine. Okay. So, these are the two important reactions of triplet carbene, which you have to remember. Okay. Now, so that is all about carbenes. So, carbenes we have seen about singlet carbenes, we have seen triplet carbenes, their reactions and how their generation. We will see now another important intermediate, which is your nitrenes, which you have not studied much. So, if I draw the simpler structure of nitrene, it should look like this, right. So, carbene is a divalent, right. So, this is monovalent, right. There is only one. So, it is a monovalent, that is divalent carbene. Just you have to compare when you talk carbene and nitrene. Same way, this is surrounded by sextet electrons. So, whether this like carbon in carbene, carbon was neutral. This is it is a charge type of charge, right, and it is more, and nitrene behaves more like an electrophile. Whenever you study nitrene, compare it with carbene, tells you much. Okay. So, again I have that 2 electrons based on the spin of this electrons. I can again divide nitrenes into 2. Okay. One I call them as so this is your singlet nitrene, this is your triplet. And again this will be working like electrophile, and this will be diradical. Right. And most of the case nitrenes are linear, okay, not like your carbenes. Carbene as this sometimes gets this trigonal planar, but nitrene most of the case they are linear in shape. Most of your nitrenes are linear. Okay. So, there is not big difference between triplet. So, most of the time they are in linear. Okay. So, we will now get into singlet nitrene now and see how singlet nitrene works. Any idea how to generate singlet nitrene? How we can generate singlet nitrene? Anyone? Come on, man. How you generate singlet carbene? You take a type of azo compound because that nitrogen goes off. Based on that idea, you generate a singlet carbene, right? So, in this case, if you want to remove 2 nitrogen out and you want to generate a nitrene, what you have to do? So, it should be a compound which has 3 nitrogens. So, what you get? Yeah, that's all. You take an azide, okay, you heat it or you thermalize or you fertilize, you end up with a singlet nitrene. Okay. This is one very good method. Okay, there are I seen like this is the only best method by which you can generate triplet nitrene. There are some other methods, but this is the best one because making azides are easy. How you make azide? If I want to make an azide, like I want to make like some azide like benzyl azide. Yeah, you just take a benzyl bromide, add sodium azide, okay, just room temperature stirring, and you get a nice. So, how you know you got azide? Any spectroscopy evidence? Yeah. Where it comes? Azide has a very distinct peak, 2100, and it will be just like your carbonyl. Like it will be, its stretching will be so huge. It's not like a small peak. It will be a very huge peak. Okay, so IR is the best way to say that you get an azide. And so, and this reaction goes like 90 to 95%. It doesn't even want to do column. Then you can fertilize them. You get a nitrate. Okay. So, if you see the reactions of this nitrene, singlet nitrene, I am taking this type of see what happens in singlet carbene. If I generate a singlet carbene, it undergoes an insertion in your sigma bond, right. So, triplet nitrene also does the same thing. It sorry, singlet nitrene also does the same thing, insertion to sigma bond, but it is much more selective. For example, I get this as a major product, CH3C. Nitrogen NHR. Okay, nitrogen. This is N, and I might get this also little bit. That is how your peptide you can insert your nitrenes into peptides. See, if I take a nitrene, okay, instead of my R, if it is for example coumarin, okay, or like perlene. Perlenes are highly fluorescent, right. So, I can make my perlene nitrene, singlet nitrene. Then if I react with my peptide, it can easily insert into my peptides, like basically protein. If you want to insert into a protein, you can insert it. Then what happens? My whole protein will be fluorescent. Then I can visualize by fluorescent microscope how this interacts, and I can start studying their that is called your fluorescent imaging. So, this nitrene has a big role in fluorescent imaging. You can that is a big field, like fluorescent probes and fluorescent imaging chemistries are a lot where you can directly visualize what is happening with your cellular level. But in this case, if you say this is your major product, the secondary one, and your primary one is very like very minor amount. So, it has some selective, not like your singlet carbene. Singlet carbene randomly does. Okay. So, singlet nitrene is not that, it has some selectivity. So, first it does gives major product with 3 degree, then it goes to 2 degree, and then your 1 degree comes in. Fine. Another thing also you should know in the insertion, particularly with nitrene, that also you can see in carbene also. Take a type of chiral carbon, okay, and does this. You know that it goes only to triplet 3 degree one. So, what happens in this case is that you get retention in configuration. Singlet carbene also gives retention in configuration, but only it is random. Okay. Triplet you can see very selective and retention in configuration in singlet nitrene. Fine. Then this part, you know, there is nothing need to talk like this. Addition to pi system, you know that now singlet will give you stereo specific product. What is this molecule which I get now after the reaction? Sorry. Aziridine, right? Aziridines are you know about aziridines, right? They are very important for agrochemicals, and they have a lot of activities. Aziridines, it's easy to make. You take an alkene, you generate your singlet nitrene, you end up with your aziridines. Azirines is or what? Azirine. Aziridine is this, azirines if you have a double bond. Okay. Yeah, you get stereo specific, that you know. Okay. Now, we will just slowly go to your, that is all about your singlet nitrenes. Okay. Triplet nitrenes, just as you said, once I fertilize, I get my singlet, and this in low temperature just like your carbene. Okay. Gets you triplet. Any other way you can think that if I can you generate triplet nitrenes? Can you think any other chemistry? I want to completely bypass this singlet nitrene. See, whenever you say it is low temperature, okay, you have an intersystem crossing singlet, then it's always will be in equilibrium most of the time. You will have singlet as well as triplet. Okay. I want to completely bypass my singlet nitrene. I want to get only triplet. You have studied this, just want that whether you can use it. No. Okay. See, I take a system like this, for example, like I take this. I fertilize now. but I photolyze in such a way that, see, azides have absorption round about 250, 270, that is all. Okay. So, I photolyze in your test tube. So, test tube is normally Pyrex, okay, Pyrex test tube, right. So, their cutoff is how much? Regular test tube. Yeah, they are starting from 290, but exactly 310 nanometer. Okay. So, what will happen if I shine light now on this compound in my test tube? I take this compound and shine light in test tube. What will happen? My azide will not absorb any light, fine. So, whatever light will be absorbed by my ketone. So, what you know about ketone? Once the ketone absorbs the light, what happens to ketone? It goes to, come on man, it goes to singlet, right. Then it undergoes a nice intersystem crossing to give me get my triplet. Then you know that there will be a energy transfer can always happen, right. So, this can do an energy transfer, which you have studied. You can have an intramolecular energy transfer. So, it can does a nice energy transfer. To give me what? Yeah. So, if it, because it is triplet azide right now, it will be in the triplet state. So, that will give me a triplet nitrene. So, I can completely bypass now my singlet. Right. This is very interesting process. Okay. Fine. So, this is how you can generate. These are the two ways. One, you can take directly your nitrene, singlet nitrene, low temperature, you can go triplet, or you can use your energy transfer concept. Okay. Reactions of triplet nitrene. For example, I am taking this compound, photolyzing this. It gets me a triplet nitrene. This triplet nitrene reacts with another molecule of triplet nitrene. To give me dimer. This type of dimer you can get. Another important reaction triplet nitrene does. Any guess? If I treat it with oxygen, what will happen? Because oxygen is triplet in ground state and my nitrene is also triplet. So, they can react. So, you end up with nitro compounds. There are many nitro compounds made. Easy to make nitro compounds like this way. You make chloride, from chloride you just use sodium azide, then become nitro, and from azide, then azide with your oxygen, end up with your nitro compound, right. These are the two main reactions of your triplet nitrene. So, just I will just now sort of summarize this nitrenes, just two reactions. This is my singlet carbene, triplet carbene, singlet nitrene, my triplet nitrene. Oh, yeah, no, sorry. So, we will see addition to pi system, how these guys work. What happens with singlet carbene addition to pi system? We have studied that. It should be very good. It should be stereo specific. This should be non-stereo specific, right? Again, this should be stereo specific, and this should be non-stereo specific. This is the important part you should know, insertion to CH bond, how it works. Singlet carbene can insert, okay, but they insert randomly. You can see little bit retention there. Okay. Triplet carbene inserts, but not that much. You can see selectivity as well as specificity. It will be selective, it will be specific. Singlet nitrene, yeah, it can insert, but it will insect selectivity, that is there, okay, and it also does retention. Triplet, no insertion, you cannot see any insertion there. Okay. Fine. Okay. So, that's all major about your organic reactive intermediates. These are the two which you study, carbenes and nitrenes most of the time. Okay then, thanks.